Alright, welcome back to another video by Firestarter Graphics and Engineering. Today we're going to go over some more computational fluid dynamics and rocket design. It's going to be a little bit longer of a video because I'm going to cover a lot of material. So sit back, grab some snacks, and enjoy. So the first thing I want to discuss today is this technical report number 11 by Estes. I mean, this was done, I don't know if it has a date on it, but it's the aerodynamic drag of model rockets. Now the beauty of this is this can be used on high-powered rockets and even very large-scale rockets. All this math and all the techniques in this report are still used today. Now, what's really cool about this report is he goes into a lot of the fluid dynamics. He goes into Reynolds number, he goes into how the drag is calculated, how empirical testing works, has some graphs, pressure drag, friction drag, a ton of things. And it's a really, really, really good report. I suggest reading all of it, but especially reading and going through, let's go through the appendix. Let's see, starting at Appendix 1, he goes through a full example of how to find the drag, the total drag of your rocket, based on the Reynolds number, the temperature, the launch site, the surface friction, everything. And so what's cool about this is if you mix this with the Barman equations, that is exactly what OpenRocket, which is another software that I use and other rocketeers use, to create rockets. OpenRocket is phenomenal. It tells you your total drag, it tells you the drag of each part. As soon as you add characteristics to the part such as smooth paint, rough surface, the type of material, it recalculates everything. Some people have asked me, would you use OpenRocket over CFD? No, because they're both CFD in a way. I mean, OpenRocket calculates all those things and also tells me the apogee, also tells me the ejection charge timing, if I'm going to put in my own gunpowder for a disposable motor, what time to set that for. There's things that OpenRocket does that CFD does not do, and vice versa. There's things that CFD does that OpenRocket doesn't do, and that's mostly visuals. It's really hard in OpenRocket to visualize what's going on with drag, but you can do that with CFD. And so today I'm going to show you, I've already shown you how to look at those visuals and create visuals, but today we're actually going to figure out how to calculate forces on our rocket using CFD. So some basic equations that we should all know if we're going to do this is the frontal area of a rocket is pi r squared. It's the cross-sectional area of the body tube plus the fins. The frontal area of the fins is just the cross-section of your fin pattern. So basically width times length, and then however many fins you have, you add that to your frontal area. Then we have this thing called Q. This is known as dynamic pressure. It is rho over 2 rho divided by 2 multiplied by your velocity squared. In the case of the rocket I use for this video, that's 25,000 pascals. Yes, 25,000. Okay, so I had to recheck some things in my head. You'll probably recognize this part from the original drag equation, which is right here, where you have your frontal area multiplied by your drag coefficient multiplied by your velocity squared times 1/2 times rho. We just call this Q, and it goes right here, and you have this. So if we solve for the drag, we end up with this down here. And the total force in the x direction for us is going to be the drag force plus the viscous force. So we need both of those, and technically that should be this right here. And so in Ondsel with the CFD workbench, we can get all of these plots. You can see the force in X, which is right here, and then the viscous, which is right here. We add those up, and that's what becomes FTX. So I want to show you how to do all of that. So let's see. Yep, I'm just going to show you from the very beginning. I'm not going to make the rocket, but we're going to set up the entire case from the very beginning. So let's get to it. Okay, so here is my rocket. Inside I have Fusion 1, Fusion 2. Last time this is what we kind of molded and glued together. So I'm actually going to rename these so that we can have something. This is going to be called airframe. That includes the nose cone. This is going to be fin can. And I know this is going to be a long video, so thank you for being patient. Okay. Rename rocket. Okay. So now we have this. So the next thing we need to do is switch to the part workbench and drop a cube. Alright. Now, like I said last time, general rule of thumb is to make at least the inlet length, the length of the chamber, to be 5 times as long as whatever you're testing. So for me, I'm just going to go 8,000 millimeters, and I'm going to do this by 3,000 by 3,000. And if you forget how to do this, remember when you click on the cube, if you look over here in the property view, you should be able to find the underneath box length, width, and height. Okay, we zoom out a little bit, we can see what this looks like. I'm going to switch to the front view, and now instead of moving the rocket into the box, I'm going to move the cube over the rocket. I have found that that seems to be a little bit easier, so I'm going to go -500. Let's zoom in just a little bit so we can see what's going on. I'm going to highlight cube, hit V for view, T for transparency. Alright. So in the Y direction, I want -1500. In the Z direction, I want 15, nope, I want negative as well, 1500 millimeters. So if we just look at that, we have, okay, perfect. Now, we are almost done. Kind of, not really. I lied. Alright, the one thing I want to do, let's see. Okay, so the next thing I want to do, instead of cutting it, we're going to try a new little trick. And I prefer this trick in case something goes wrong and I can always go back. So I'm going to highlight both the cube and the rocket, and I'm going to make a compound. I'm going to go over here, click this, make a compound. That's what I want. Okay, the next thing is a little bit more advanced, but it's a simple concept. We're going to make a volume refinement. Last time we did a surface refinement where we just refined the mesh around the surface. But this time we're going to do a volume refinement. So we're going to drop a cube again. We're going to rename this refinement. And let's see, the X direction, I want this to be 1500 millimeters in length. Wait. Whoops. That was position. Haha. Okay, let's put that back to 0. Let's scroll down until it says box. Do the length of 1500. Okay. The width, I want, each fin is 100 millimeters. So let's try 500. In each direction here. Okay, now we're going to take this cube, it's called refinement, hit V for view, T for transparency so we can see it, and now we're going to put it in place. So on the x-axis position, I need to go -250, and I want to go down negative, nope, I want to go down negative, let's see, 250. Let's do 250 all around and see how that does. Does that put us right in the center? It does. Okay, perfect. So now we have a rocket right in the middle of this volume refinement. And what this is going to do is, in the CFD, we're going to use this to where it's going to refine the mesh all around this area. So it's going to be super fine mesh for a larger area. So it's going to be a little bit more accurate. So far, so good. And I think we can now move to the CFD portion. So move to the CFD workbench, drop an analysis container, open it up. Let's go to the physics model. We're going to stick with steady single phase isothermal with viscous. We're going to switch to RANs, keep the model at K omega SST. We're going to hit OK. We won't worry about high Mach numbers yet. I'm getting some errors anytime I do that, and I need to figure those out before I can show you guys how to do a more advanced tutorial. Okay, let's go to fluid properties. We're going to keep it at air. Let's go ahead and hit OK. And then initialize fields, potential flow, everything looks good. Hit OK. Alright, I'm just going to see this blue little check mark. I'm going to hit this right here for refresh. Goes away just to make sure everything is good. Alright, I'm going to do my boundaries now. I'm going to click on the front. I'm going to make an inlet, uniform velocity. It's already has the face selected from the list. In the X direction, we're going to do 203 meters per second. Hit enter. Let's double check it. Okay, yep. It puts it back to millimeters per second. That's fine. Hit OK. Grab the back end. It's going to be an outlet, static pressure. Hit OK. And then, next we're going to grab each wall. So hit Control, select each one. Just remember to let go of Control as you rotate in Ondsel. Okay, so now we have our wall selected. Go ahead, hit wall, no slip. Everything's good. Go ahead and hit OK. Alright, the next one we need to add is we're going to hit just boundary layer. It's going to be called a wall, and we're going to select from list. And we want to select airframe and the fin can. That is our rocket, or at least in my case, my rocket. And hit OK. And you'll see why we did this. Now I can leave it as wall 001, but I'm going to rename it as to wall _ rocket. So now I know exactly what that is. Okay, we are almost there. I'm going to refresh again, make sure everything's good. And I'm going to click on the refinement. Nope. So I need to go up. I need to click on the compound. We're going to drop a mesh in here. We want CF mesh, and I want a little bit finer. I want 100 millimeters again. That's okay. Alright, everything's good there. Hit close. And then let's do mesh refinement. And open this up. On mesh refinement, we're going to do a volume refinement at 0.5. And if you click, make sure when you click out of it, you don't see. If you click over here and up here, see how it changes that? That's annoying, but that's okay. Select from list, click on refinement, go down here and hit solid, and then hit OK. Notice everything is disappeared, so we need to turn everything else back on. That is, I don't know why it does that, but we turn everything back on so we can see it. Okay, now, and the fin can is somewhere. Okay, it's just hard to see. Alright. Okay, now we're going to go back to compound mesh, and then we're going to put in another mesh refinement. And on this one, it's going to be a surface. It's going to be 0.1. And then we're going to select from list, and we're going to do airframe and fin can. Okay, so once airframe and fin can are selected, and we have set this to our relevant size, don't worry about refinement thickness at the moment, so just hit OK. So now we have two refinements, all of our walls, our physics model, and the last thing we need to throw in there is this little guy right here called reporting function. You're going to click it, and it's going to say, what do you want to report? Forces or the force coefficients or the probe. So we're going to do forces. And then from the patches, you're going to do wall rocket, hence why it was important to label that. What this is going to do is calculate the forces hitting against that patch that we've created, which would be right against our rocket. Okay, parameters. The relative pressure reference. That is the 25,000 that we calculated. Now, in a closed environment like this, this relative pressure reference doesn't really matter, but if this was an open far field, that would be different and it would matter, but I always put it in just in case. Everything else I can leave. Okay, so at this point, everything, cross your fingers, should run just fine. So let's go ahead, scroll down, go to our compound mesh, double click it, hit write mesh case. It's going to take about 10 seconds, and then hit run mesher. This should take about 10 seconds. Okay, and we're done. Now, let's go ahead, go up to the CFD solver, click it just once, go down here and change it. You can leave max iterations at 2000. It should complete within 200 on this one. Parallel cores, I'm going to do 8. And then double click, hit write mesh case. And then I'm going to show you something. Go ahead and hit edit. And let's look at the 0 folder. Nope, I lied. Go back to case, go to system. This control dict file, right click, edit with Notepad or Notepad++. Notice the application is simple foam. That's what we want. We don't want to deal with high speed aerodynamic solver yet, which is HISA. We'll get there eventually. And then if we go down, you can see functions, reporting function, and you can see the 25,000 we've put in there and whatnot. So this is good. Eventually you'll learn how to deal with these files on your own. I don't really go into too much of it. Okay, so we've written it, and now we're going to hit run. So you can see down here, it's running, it's creating the mesh, and now it's doing its thing. I just want to show this before I pause it. Okay, it's going to start its there we go, reporting function, and the residuals plot. I'm going to go back to reporting function. I'm going to move this down here, right there, which will then turn the screen. So I'm going to go back to reporting function, and you can kind of see now it's solving for the pressure and the force of the pressure in the x direction and the viscous force. So whoops, now I'm going to put that back up there. Okay, now we can see, and it should generate this plot right here. Okay, and then we're going to calculate our values. So let's go back. Shouldn't take too long. I think this is 100 right here. If I have done it right, this should be 100, and then this would be, I think we're going to get close to 114 newtons. I've ran it so many times. So I'm just going to let it go ahead and finish, and I'll be back. Okay, so it went ahead and finished. It took about 3 minutes total, so not too bad. So at the very end right here in the reporting view, you can scroll up just a little bit and see the sum of the forces. We have 113.7, so I'm going to round that up to 114. Now, if yours doesn't show this, you're like, oh man, where do I see my forces? That's all right. Go back into the solver, and since I haven't closed it, I'm going to go ahead and hit edit, and Remember how I told you to create that CFD data dump folder and it writes a case and a mesh case? Go to your case. Now go to your post-processing reporting function 0 force.dat, right click, edit with notepad, and you can see total in the X, total in the Y. So scroll all the way down. We did what, 137 iterations? So it says 1.13, but E plus 2. So that is 1.3 times 10 to the second, or 100. So 113.7. So literally move decimal 2 places. And we have 113.7 or 114 newtons. All right, that's good. So now you have a pretty graph that you can cut out and put in a report if you want. Which is this. You can look at simulation residuals and see how, what was that about? Iteration 80. We had this little plateau and then it dipped. So what does that do in the reporting function? Oh, okay, that's when it's always been increasing, so stayed constant here. Oh well. Okay, so now what do we do? Well, what you do now is either use a calculator or do it by hand, but I just use Omni Calculator, the drag force. We know the density is 1.25. We know our velocity was 203 meters per second. We don't know our drag coefficient. We know our area was 0.0093, and we know the total force was 114 newtons, and look, 0.4759. Now, in open rocket, I gotta remember, is this a 4-fin or a 3-fin? This was a 4-fin rocket. Okay, in open rocket, when I designed this rocket, I got a drag force of 0.51. So, actually that was with 3 fins. Nope. 3 fins was 0.4. Yes. Okay, so, yes, got a very similar, I'm trying to remember. It's like 0.49 or 0.51. Anyway, really close to what we have. So not bad. And the cool part, now you've watched my other videos, you can actually go back. So I'm going to go ahead and close these. Now you can go into pair view and do some cool stuff and, and make a slice here, make a slice there, or just do the stream chasers and just see how things are done. So if we were to do, I'm just going to put a slice in the, scroll down in the Z normal. Sure. I'm going to hit apply, and I'm going to hit don't show the plane. Going to go to the last timestamp, click up here. Okay, we're looking at, don't turn, okay. Yeah, you can see right here, and then the wake back there. Let's go to, that's the pressure. Let's go to the velocity in U. That's actually kind of cool. You can kind of see the wake left behind. Alright, there's not enough high speed to cause any of the jet streams to go kind of at the angles. But yeah, pretty cool. Now you can follow the other videos to do the other techniques to get the streamlines and all that fun stuff. In fact, let's just get rid of the slice. I'm going to come up here. Okay, let's see. I've got to remember how, once you load it, straight from, I never load it straight from the, oh, here we go. Patch, let's see, I'm going to get rid of the internal mesh. I'm going to go patch wall rocket and hit apply. See what happens. Okay, good. That's the one I wanted. Then I'm going to switch back to here. Go to the omega, just kind of see what it looks like. I'm going to switch to surface LIC. Hopefully this won't crash it, but it might. Okay, there's the pressure. And surface LIC should be, I wonder why it's doing that. I'm going to delete that one. Okay, let's open that up. Okay, now go to surface LIC. Okay, yeah, see, I don't know why ParaView does that to me. Right when I import it from Ondsel, I can never get surface LIC to work. But if I open up the pv.foam like I showed in the other videos, it works just fine. Anyways, you know how to do all that stuff. But, oh yeah, one other thing is I sealed the rocket in the back because it was bugging me. But you can kind of see it's pretty cool, pretty cool. Okay, anyway, I just wanted to mess around for a minute and just kind of look. But yeah, so not too bad. You guys learned some new advanced stuff, learned how to calculate forces in Ondsel Engineering Suite. So the next one we'll go into using an open far field, because then you don't have to generate a mesh as much, and the only thing you ever have to change is just a velocity in one direction, and sometimes it's a little bit easier. But you use far field when you're dealing with high Mach numbers. But every time I run it, something happens and it errors out. So once I figure that out, then I'll show you how you guys do it. Anyways, thanks for watching. I hope you enjoyed, and I hope you learn lots of stuff. Go read that technical report and follow along, especially in the index, not the index, the appendix. Write it. Do yourself a favor. Grab a, what is it? Let's see, what am I looking at here? Just an, you can get them at Walmart. It's an 8.5 by 11 sketchbook for like $4, completely empty, has a wire ring, and it's used for sketching. But use that for calculations and drawing. Go through the technical report, write down the equations, do things, go through the appendix number 1, and print off the report, or at least the graphs that you need for appendix 1 exercise. Go through it, learn how to use those Reynolds numbers tables, and find the drag of your rocket from the very beginning to the end. Just pick a model rocket and find it. I did it for this rocket for a master's project, and it was really cool, and I got 0, like within like 1 decimal place. It was amazing how cool it was, and to open rocket. So I love doing that stuff, but it's really worth learning and going through and doing hand calculations just to see how it's done. And then it just solidifies the information more. And if you've never used OpenRocket, go get it and start learning how to use it. It's really cool and does a really good job at CFD in a way, a numerical kind of method way. Anyways, thanks for watching. Enjoy, and see you next time.